Hello, I'm going to introduce the paper about decoupling cores, kernels, and operation systems. This paper presents a Barrelfish DC, extension to the Barrelfish OS, which decouples physical cores from native OS kernel, and furthermore, the kernel itself from the rest of the OS and application state. In Barrelfish DC, native kernel code on any core can be quickly replaced. Kernel states move between cores, and the cores added and removed from the system transparently to applications and OS processes, which continue to execute. Before I introduce the whole paper, I would like to show a short outline about this presentation. First, I will introduce motivation about trends in hardware and software. The next part is implementation on booting and shutting down cores dynamically. The rest of the paper, which is about evaluation and conclusion, will be given by my partner. So, what's happening to the hardware? Today, we are mostly constrained by power consumption. This will bring us, for example, reconfigurable cores, which means we can dynamically change behavior. So this is what we already do today, like DVFS, which means dynamic voltage and frequency scheduling, and turbo boost, and also SMT. There's also some research technique like core fusion, which allow us to fuse multiple physical cores into simple, more powerful core, or split them up again. On the other hand, the future may have to do dark silicon, which means we can have many cores, but we cannot power them all at the same time. So what does it mean for us for adding and removing cores in the system? Well, we already do it today. For example, if cores fail or if reallocates cores to different machines. On the other hand, you may take cores out of service because we will not power them all at the same time. Also, there's heterogeneous cores. Heterogeneous cores in our machine giving us a symmetric performance. And for example, one such logical conclusion of this would be conservation cores. Now, we imagine we build an OS in a dark silicon area. So you have set heterogeneous cores, and you need to switch between the cores based on your workload. But you also need to power down and take cores out of service because you don't have the power to pack everything at the same time. So this is the current model today. The current runs as a single program in all cores, and every course run the same code, and it's hard to adapt like heterogeneous cores. So what happens if you move a core in such a system? Well, we have to go deep to the data structure to reflect this change. Typically, this requires global coordination, and also the data structures may be globally shared protected by locks. What happens if processor holding analogs? So there's a lot of issues there. And what's happening to software? In software, we usually need to adapt to different workloads in our OS. Now, general purpose kernels are very useful to adapt, but we still have to adapt to modify build, boot, and runtime. For example, to facilitate debugging with profiling and tracing. And sometimes application requirements are very strict, such as real-time support, and it's hard to adapt everything into general purpose kernel. Now, there are also research techniques that work by modifying or upgrading cores on the fly, as is the case, for example, Ksplice in Linux or K42 upgrade mechanism. So, we argue that a good architecture model dealing with dynamic cores or adapting to heterogeneous cores or changing software requirements is a multi-kernel model. In a multi-kernel model, each core runs separate kernel programs, and the state is currently in per-core state into what we call OS node. Now we still have to run applications on the top of that, and applications may share state between cores. Therefore, we replicate the state between cores using asymmetric message passing. So, however, a multi-kernel model is not enough dealing with dynamic cores. So we still need to deal with OS node. So I'm going to so we use as a basis with Barrelfish is an implementation of multi-kernels, and we add some features to multi to Barrelfish. That we call the Barrelfish DC, which I mentioned at the beginning. Treat cores as much as possible as pluggable device. So we will next of how we booting a core dynamically with boot drivers and how we shut down a core in system. We use the technique that externalize kernel state that allow us to decouple cores, kernels, and operation systems. Um, After introduce the rest of the implementation, we should mention that I should mention that the paper focused entirely on mechanisms in this paper. So don't address scheduling and the policy for kernel replacement, core power management, or application migration. Note also that this paper main motivation in Barrelfish DC is adapting the OS for performance and flexibility. So this paper doesn't consider fault tolerance and isolation. First is about booting a new core. Bring a new core online is a question of turning on, updating this table, and creating per core state when needed. Previous version of Barrelfish also adapted this approach and booting all cores during system initialization, though there has been experimental work on dynamic booting of heterogeneous cores. Barrelfish DC targets a broader hardware landscape with complex machine comprising potentially heterogeneous cores. Furthermore, since Barrelfish DC runs a different kernel instance on each core, there's no reason why the same kernel code should run everywhere. So we need an OS representation of a core on machine which abstracts the hardware dependent mechanism for bring the core up and down. Therefore, Barrelfish DC introduced the concept of a boot driver, which is a piece of code running in a home core, which manages a target core and encapsulates the hardware functionally to boot, suspend, resume, and power down the later. Currently, boot driver runs as a process, but closely resemble a device driver and could equally run as software objects within another process. A new core is brought online as this 5-step. First is the new core is detected by some platform-specifically mechanisms, and its appearance registers with the device management subsystem. The second step is Barrelfish DC select and start appropriate boot driver for a new core. Barrelfish DC selects a kernel binary and argument for a new core, and directs the boot driver to boot the kernel on the core. The first step is the boot driver loads and relocates the kernel and executes the hardware protocol to start a new core. The new kernel initializes and uses existing Barrelfish protocol for integrating into running OS. Booting a core in Barrelfish DC only involves two processes: the booting driver on the home core and the kernel on the target core. For this reason, we require no global locks or other synchronizations in the systems, and the performance of this operation is not impacted by loads on other cores. And next is about shutting down a core. It's much harder than booting a core because we need to deal with poor core states, like we need to take more space for scheduler queues and memory pool, also the page tables. It means we need more time and energy. However, we want to remove the core as fast as possible. The general approach that follows, like Chalimans, is getting state out of the way quickly and dismantle it later or lazily. So how did it work in our OS? First, we close them away, and we are able to capture this OS or all per core state, and we move it to a different core. Now, we add an OS scheduler into kernel that is able to dispatch the different OS node. And we call this core one OS node removed to a kernel that already have an OS node, temporarily parking OS node. And we can already notice here, this approach is highly scalable, as we only involve two cores in process right now. We don't need to normally coordinate it in this system. So what happened next? We can either move back to previous cores or to move it somewhere else. And we should pay attention. What is the OS node? And how do we capture this OS node? This is typically not clear in OS. Per core state is not explicitly defined and typically have many different states data structure. So in this paper, they use partitioned capability system to explicitly capture OS nodes, meaning entire per core state in a single data structure. First, I want to introduce about the frame and SQL in the partition capabilities. Capabilities are typed to reflect what the memory is used for. A frame capability refers to memory that the holder can map into their address space. C-node capability refers to memory that is used to store the bit representations of capabilities themselves. So this captures all accessing information and memory allocations about applications. So all per core states in the kernel are now be accessed to this structure or reconstructed from the capabilities trees. We still need to be able to reach this structure and pass it around our system. Therefore, we add a KCB or kernel control block. KCB combines some states that don't need to persist across the kernel start. KCB is also a capability itself. It means we now have a representative handle in system to move entire per core state or out. So this method of state externalization and dynamic core booting is much more general mechanisms because we are now able to move per core states around internally in our system, and we can also replace the kernel dynamically on OS node. Also, I want to talk about how to deal with the interrupts. In general, interrupts distinguished into three types of interrupting in systems like handle local to cores and the CPU driver like timer. Also the interprocessor interrupts which set between OS node, and also the device interrupt. So what happens if we have a device interrupt? A device that runs on some cores and is migrated to a different core. Right now, we essentially marks all the interrupts and on the core, and then we have to register the interrupts on the device driver. So we typically doing this process is sometimes happen between you have to go and check again if something happened into device, or you can pull the device while doing this shift. Okay, welcome to my partner to introduce the rest of the paper. Thank you.
We present here a performance evaluation of Barrelfish. First, core management. We measure the performance of starting and stopping cores in Barrelfish and in Linux. Second, applications. We investigate the behavior of applications when we restart kernels and when we park OS nodes. Third, performance isolation, specialized kernels. We demonstrate isolating performance via a specialized kernel. Fourth, kernel updates. While performing this evaluation, hyperthreading, turbo boost, and speed step technologies are disabled in machines that support them, as they complicate cycle counter measurements. Core management options. In this section, we evaluate the performance of managing cores in Barrelfish and also in Linux using the CPU hot plug facility. We consider two operations: shutting down a core and bringing it back up again. Bringing up a core in Linux is different from bringing up a core in Barrelfish. In Barrelfish, each core executes a different kernel which needs to be loaded by the boot driver, while in Linux, all cores share the same core. Furthermore, because cores share state in Linux, core management operations require global synchronization, resulting in stopping application execution in all cores for an extended period of time. Stopping cores is also different between Linux and Barrelfish. In Linux, applications executed in the halting core need to be migrated to other online cores before the shutdown can proceed. While in Barrelfish, we typically would move a complete OS node after the shutdown and not individual applications. Stopping cores. The cost of stopping core in Barrelfish is about 0.8 microsecond. Barrelfish does not share state across cores, and as a result, no synchronization between cores is needed to shut one down. The cost of shutting down a core in Linux ranges from 46 milliseconds to 131 milliseconds. More importantly, the shutdown cost in Linux explodes when applying load, while it generally remains the same for Barrelfish. For example, the average time to power down a core in Linux on Haswell machine is increased by 55 times when we apply load. For Barrelfish, the setup cost in boot driver dominates the cost of starting a core. The figure shows a breakdown of the cost for bringing up a core on Haswell machine. Barrelfish has to prepare the kernel image when idle. The cost of bringing up a core for Barrelfish is similar to the Linux cost. Applications. In this section, we evaluate the behavior of real applications under two management operations: restarting, where we update the core kernel as the application runs, and parking. In parking, we run the application in a core with a normal kernel and then move its OS node into multi-KCB kernel running on a different core. While the application is parked, it will share the core with another OS node. First, Ethernet driver. In this experiment, we use ping command from a client machine to send ICMP echo request to the NIC. The figure shows the effect of the restart operation in the round trip latency experienced by the client. Initially, the ping latency is 0.042 milliseconds on average with small variation. Restarting the kernel produces two outliers. packets 2307 and 2308 with an RTT of 11.1 milliseconds and 1.07 milliseconds respectively. When parking begins, we observe an initial latency spike from 0.042 milliseconds to 73.4 milliseconds. The spike is caused by the parking operations, which involve sending a KCB capability reference from the boot driver to the multi-KCB kernel as a message. After the initial coordination, outliers are only caused by KCB time sharing. After unparking the driver, latency returns to its initial level. Unparking does not cause the same spike as parking because we do not use messages. We hold the multi-KCB kernel and directly pass the KCB reference to a newly booted kernel. Second, web server. In this experiment, we examine how a web server that serves files over the network behaves when its core is restarted and when its OS node is parked. We initially transfer on client machine in the server's LAN using wget command and plot the achieved bandwidth for each 50 kilobytes chunk when fetching 1 gigabyte file. The figure shows the result for the kernel restart experiment. The effect in this case is negligible on the client side. Parking leads to number of outliers caused by the KCB time sharing. During parking, the average bandwidth is slightly lower with a higher standard derivation. Third, PostgreSQL. We run a PostgreSQL database server in Barrelfish using TPCH data with a scaling factor of 0.01 stored in an in-memory file system. We measure the latency of repeated CPU-bound query. Before rebooting, average query latency is 36 milliseconds. When a restart is performed, the query has a latency of 51 milliseconds. After a few queries, the latency returns to its initial value, shows the effect of parking the OS node that contains a PostgreSQL server. When the kernel is parked, we observe two sets of outliers, one with a latency of about 76 milliseconds and one with a latency close to 56 milliseconds. This happens because depending on the latency, some queries wait for 2 KCB time slices of the co-hosted kernel, while others wait only for one parking. As expected, causes a performance degradation, especially for a latency critical applications. Furthermore, with improved KCB scheduling algorithms, the performance degradation can be reduced or tuned. Kernel update. First, we shut down the target core. Then we reboot the core with a new kernel image and passing it to the previous OS node. From an application perspective, this will just look like the application has not been scheduled for a while. To evaluate the use case, we have running PostgreSQL with TPCH database inside the OS node, and we measure latency of queries on y-axis and query over time on x-axis. At some point, we hot swap the kernel and see this produces some outliers because we actually need to reboot the core, so outliers are all about 10 to 15 milliseconds. Specialized kernels. To evaluate a real-time application use case, first we shut down the core, then we're going to move OS node and temporarily park it on another core. So we can now free up space on the core. So here we again have a PostgreSQL instance with a TPCH database inside an OS node. And on the first part, we have one OS node per core, and the response time is about 40 milliseconds. At some point, we temporarily parked OS node. Currently, OS node share time on the core, therefore the latency increases up to 80 milliseconds. Afterwards, we move OS node back to its original core, and the query response time normalizes again. Now we have freed up one of the cores. We can boot this core with special kernel and build a simple real-time kernel that essentially does not take any interrupts. It does not have any timer or scheduler in the kernel. It is designed to just run single application, So this kernel constructed on OS node and temporarily run a real-time application. To evaluate the performance isolation that can be achieved with a specialized kernel compared to the isolation provided by an unmodified Barrelfish kernel and Linux 3.13 kernel. To measure OS jitter, we use a synthetic benchmark that only performs memory stores to a single location. We sample the timestamp counter every 1000 iterations for a total 1 million samples. This figure shows a histogram of sample cycles where for all systems, most of the values fall into the 6 to 7,000 range, that is 6-7 cycles latency per iteration. The Barrelfish dedicated kernel, where all the samples are in 6,000 to 7,000 range. In Linux and Barrelfish, we observe significant outliers that fall outside this range. We conclude that Barrelfish enables the online deployment of a dedicated, simple-to-build OS kernel that eliminates OS jitter. Future work and applications. OS nodes are an entire per-core state. If you want to move between power-efficient and high-performance core, as a kernel developers interested in dynamic OS instrumentation, for example, profiling, tracing kernels, which we can simply do now by swapping kernels with a debug kernel. Also to test impact of some features having the kernel can simply swap kernels to do A/B kernel testing. Specialized kernel to run application in guess ring 0. With this method, it can simply run this Arrakis OS on some of the core and move it back later. Conclusion: Barrelfish presents a radically different vision of how cores are exploited by an OS and the applications running above it, and implements it in a viable software stack. The notion that OS state, kernel code, and execution units should be decoupled and freely interchangeable. Barrelfish is an OS whose design assumes that all cores are dynamic. As hardware becomes more dynamic and scalability concern increases, the need to partition or replicate state across cores, system software will have to change its assumption about the underlying platform. For many versions of dark silicon hardware, this may be the only way for system software. Thank you.